In this video, we're going to talk about an application using our idea of linearization, that tangent line approximation. We're going to use it in what's called differentials. So the Leibniz notation for a derivative, dy dx equals f prime of x, when Leibniz came up with that, he never intended for the dy and the dx, those are what we're going to call the differentials, to actually be separate quantities, and where you could multiply one to the other side. But they were just intended to represent this limit as delta y over delta x as delta x goes to 0. That is, our f of x plus h minus f of x all over h. It was just supposed to signify and remind you that that's where that derivative came from. But it turns out we can get away with this as long as we don't get too crazy, as long as we can make sure that we can get back to dy dx is equal to f prime. So our definition is we're going to say let f of x be a differentiable function. The differential dx is going to be an independent variable, so we can choose it to be whatever we want. The differential dy is we're just going to multiply that dx over. So if you looked at this dx here, if you just multiply that to the other side, then that's how we get this expression, the differential dy is equal to f prime of x times dx. So dy depends both on what x is as we plug it into f prime and on what we choose dx to be. So we're going to do some examples here. I'm going to slide this screen up a little bit. So we're going to do some examples first just on kind of the mechanics of it. How do we actually do this stuff? And then we'll try to get into some more application type of stuff, which of course gets a little bit more challenging. So on the first one, we're told that our function y is equal to x to the fifth plus 37x, x is equal to 1, and dx is equal to 0.01. So we start by finding the derivative, dy dx. That's going to be just as we've done before, 5x to the fourth plus 37. From there, we're going to multiply the differential dx to the other side. So this is the kind of interesting new and different strategy. So we can separate out the dy and the dx. Now we're just going to plug in the values for x and the value for dx. Since x is 1, 5x to the fourth is going to be 5 plus 37, and we're using 0.01 for the differential dx. So that's going to be 42 times 0.01 is going to be 0.42. So we would say the differential dy is equal to 0.42. That's it for now. So like I said, we're just doing the mechanics of it. So let's try it again. Now this time we have y is equal to sine 3x. So we start by finding the derivative. This is a chain rule derivative. So the derivative of sine is going to be cosine of 3x, and then times the derivative of the 3x is going to be 3. We will separate the differentials, so we will multiply that differential dx to the right side and get the differential dy is equal to 3 cosine 3x times dx. Then we're going to plug in, we're going to plug in the numbers that we know. So the x value is going to be pi, so we're going to get 3 cosine of 3 pi times the negative 0.02, that's our differential dx. So cosine of 3 pi, if you remember, is going to be negative 1. So we're going to get a negative 3 times a negative 0.02, and that's going to be a positive 0.06 for our differential. Now, the next one is kind of interesting because we're going to have to tie in here a little bit of our implicit differentiation. So we have differentiating here, we're going to get the derivative of x is 1, plus we're going to get dy dx, that's what we're going to call the derivative of y. And now we're going to do a product rule derivative. So we're going to get the first times the derivative of the second plus the second times the derivative of the first, and the derivative of x is just 1. So let's see what we know here. Let's plug in what we know and see if we can solve for dy eventually here. So we have 1 plus our differential dy we don't know. The differential dx is going to be 0.05. That's going to equal, the x is 2 times, we're going to get the differential dy, and then time over the dy over the differential dx, which is 0.05. Now we don't know why. Well, let's solve for it back up here. So back here we had 2 plus y is equal to 2y. So subtracting y from both sides, we're going to get that y is actually equal to 2. And so that's going to make that be a plus 2 over here. So let's see, how do we want to do this? Should we subtract the 2 to the other side, and then we can move this dy over 0.05 to the other side. So that's going to make that be a negative 1 on the left side. Subtracting the dy over 0.05 from the 2 dy over 0.05s is going to leave us with one of those differential dy's over 0.05. And then we can multiply that 0.05 to the other side and get negative 1 times 0.05 is a negative 0.05. So there's the mechanics of it. So let's turn the page here and see some more examples. So let's take a look at what we're going to do, the idea behind our linearization and how we can use differentials to estimate that change. So if we look at this curve, we have this y equals f of x. We pick a point there, x equals a, and then we're going to imagine now the tangent line to that curve is going to look something like that. Then we imagine that we come over a little ways from a, and we're going to say we're going to move over a delta x away from a. And what we would like to do is find an approximation to the actual value of the function right there on the curve. But what we're going to do instead is use our tangent line and move over that delta x and find this value as that approximation. That is, what we are interested in is this, the actual change in the value of the function to the function value at the new point would be delta y. We know that the slope of this tangent line is our derivative, which is dy dx. That's, we're thinking of that kind of as a rise over run here. So using that tangent line triangle here, if we choose the dx to be equal to that delta x, so it's this horizontal distance here, then this distance right here, that little blue vertical stretch, is going to be our differential dy. So what we're saying is that we're going to approximate that delta y by using the differential dy. And it's kind of strange. I mean, it's hard to, at this point in time, figure out why we might want to do that. But the idea is we're going to use this line, this tangent line, which is a very, very simple function to approximate the value of what might be a much, much more complicated function. And so it's just a matter of doing it more simply. Okay, so that's our idea. So let's kind of explore what that might look like. So we have the radius of a circle increases from 10 centimeters to 10.1 centimeters. Use differentials to estimate the increase in the circle's area, which we're going to call area A. Compare this estimate with the true change in the area delta A. Okay, well, let's unpack a little of this. We know that the area of a circle is pi r squared. We know our r our R is changing from 10 to 10.1. So we know that our delta R is 0.1, and we're going to choose our differential dr to be equal to that. Remember, dr is an independent variable, so we can choose it to be what we want. We're interested in finding the delta area, but we are going to approximate that with our differential of the area, dA. So let's see. If we differentiate our area with respect to r, then we're going to get dA dr, that's the derivative of the area, and r is our independent variable, so that's going to be 2 pi r. So we can multiply that differential dr to the other side. So we're getting the differential dA is equal to 2 pi r times dr. Now the value of r is that nice value that we knew from the beginning, that's the 10. So we can now plug this in to our differential and say that the differential of the area is 2 pi times the radius is 10, and we said the differential of the radius, dr, is 0.1. So the 10 times the 0.1 is just 1, and so we're going to get 2 pi is that approximation for the change in the area. So we would say the change in the area as we increase that radius from 10 to 10.1 is going to be about 2 pi. So I'm going to slide the screen up here a little bit, and we're going to talk a little bit about some of these ideas about some new symbolism and kind of vocabulary here that we're going to need going down the road here. So we will sometimes refer to the dr or the delta r as the measurement error. So that might be, we were trying to measure a circle, and maybe it was either actually 10 and we measured it as 10.1, or it was actually 10.1 and we measured it as 10. But our ability to measure it precisely because of whatever instruments or whatever was not exact. Then in that case, that delta area is going to be an approximation to what's then called the propagated error. So the propagated error is, once we have a faulty measurement, how does that computation of the area then magnify or carry that error forward? So sometimes that's referred to as a propagated error. So we can actually figure out the delta area in this case, because we can take that pi times 10.1 squared minus 10 squared. So that's how the area does actually change if the radius goes from 10 to 10.1. And that's going to be, and you could do that on your calculator, is going to be 2.01 pi. And so then our approximation error, if we wanted to know that, so that actual approximation error was the 0.01 pi. That's the difference between what we were using for a radius versus what it was, or how that radius changed. We can get a relative change or a relative error if that's what we're referring to. So relative change is going to be how our area changed. So if we were doing it exactly, it would be the delta area over the area. So that's going to make it into some kind of a decimal. We will approximate that with a dA over A. And then we can get to a percent change, or it might be a percent error. If we were talking about a measurement error, then we will take that delta area over the area and multiply it by 100, or we can approximate it with our dA, differential A over A times that 100. Okay, we're going to make a new video, and we're going to do some kind of challenging examples there to kind of flesh that out, but I'm going to do it on a separate video with our differentials worksheet.